This episode of The Deep Dive is brought to you by Mindful Moments. Nourish your mind on the go. A series of AI-narrated meditations designed to feed your intellect and challenge conventional wisdom.
Yes.
Each bite-sized episode is packed with thought-provoking ideas, surprising facts, and insightful analysis, all designed to spark your curiosity and expand your understanding of the world.
Ever considered that just looking at something could change what it's actually doing?
It sounds like a riddle, doesn't it? But it's not.
No, it's apparently a fundamental quirk of the universe, especially at the tiniest scales. And that's what we're exploring today.
Exactly. We're diving into quantum mechanics,
Yes.
specifically the famous uncertainty principle. It really does challenge how we think things should work.
And we're leaning heavily on the insights from Richard Feynman, Matthew Sands, and Robert Leighton in their, legendary Feynman Lectures on physics. Volumes 1 and 3 are our guides here.
Right. So the idea is by the time we're done, you'll hopefully have a better handle on why measuring things at the quantum level isn't straightforward.
Yeah, why there are these built-in limits and what that means for, well, everything.
Profound implications, really.
Okay, let's start with that classic experiment, the two-slit experiment. Imagine firing electrons, tiny particles, at a barrier with two openings. What happens on the screen behind it?
Well, if they were just tiny baseballs, you'd expect two distinct bands, right?
Yeah.
One for each slit.
Makes sense.
But that's not what happens. You actually see an interference pattern. Lots of bands, light and dark, spread out.
Interference. Like waves. Like ripples in water crossing each other.
Exactly like that. It strongly suggests each electron is somehow behaving like a wave, going through both slits at once and interfering with itself.
Okay, hold on. Each electron goes through both. That's already weird.
It is. But it gets weirder. What if you try to see which slit an electron goes through? Say you put a little detector, maybe a light source, right near the slits.
Logically, you'd find out, okay, it went through this one or that one.
You do find out.
Yeah.
But the moment you know which slit it went through,
Let me guess, the pattern changes.
the interference pattern completely disappears. Gone. Instead, you see just those two bands you originally expected for particles.
Whoa, so just watching forces them to act like particles, not waves.
It seems that way. The very act of measuring its path, finding its position well enough to know which slit, fundamentally alters its behavior. It's like it knows it's being watched.
That's the observer effect we hear about. It's not just that our measurement is clumsy and bumps it, it's deeper.
It's much deeper. And this leads directly into the uncertainty principle itself. Mathematically, one common way to state it is x times ape is greater than or equal to divided by 2.
Okay, symbols, let's unpack that. X, that's uncertainty in position, like how fuzzy our knowledge of its location is.
Precisely. And ape is the uncertainty in its momentum. Momentum is mass times velocity, basically how much oomph it has and in what direction. So ape is the fuzziness in that.
And that H with a bar.
That's the reduced Planck constant. It's a fundamental number baked into the universe, and it's incredibly, incredibly small.
So the uncertainty in position times the uncertainty in momentum has to be at least this tiny fixed number. You can't make both uncertainties zero at the same time.
Exactly. There's a fundamental trade-off imposed by nature. The more precisely you pin down the position, make it smaller, the less precisely you can possibly know its momentum, it gets bigger, and vice versa.
And crucially, this isn't just because our rulers or speed guns aren't good enough yet. We can't just build a better machine to beat this.
No, that's the key point Feynman stresses. It's not a limitation of technology. It's inherent to quantum reality. It's a law of nature.
So how does that tie back to the slits? Why does finding the path kill the interference?
Well, to know which slit the electron went through, you have to measure its position quite accurately.
Right.
Make small enough to distinguish left from right.
Okay.
But the uncertainty principle dictates that doing so must introduce a large uncertainty in its momentum.
Yeah.
That inherent kick of uncertain momentum is enough to scramble the delicate phase information needed for the wave interference. It washes the pattern out.
Ah, I see. The act of measuring position gives it an unpredictable momentum nudge, destroying the wave behavior.
You got it.
Now, some people think this just means, I can measure position perfectly, then momentum perfectly, just not at the same instant. But Feynman pushed back on that simple interpretation, didn't he?
He did. He argued it's deeper. It's not just about limitations on measurement. It suggests that maybe, at the quantum level, a particle doesn't even possess a perfectly definite position and a perfectly definite momentum simultaneously. The concepts themselves might be blurry.
So it's not just what we can know, it's about what's real at that level.
Potentially. Yeah. Feynman put it quite starkly. He said something like, just because we cannot measure position and momentum precisely does not a priori mean that we cannot talk about them. It only means that we need not talk about them.
We need not talk about them, meaning maybe trying to force our classical ideas of definite properties onto quantum objects is the wrong approach entirely.
That's the implication. It forces us to confront the fundamentally probabilistic nature of the quantum world. It's not just a limit. It's a description of how things are.
And this uncertainty, this probabilistic view, it's not just some weird footnote, right? It's central to the theory.
Oh, absolutely central. The uncertainty principle is a cornerstone of quantum mechanics. And quantum mechanics is arguably the most successful scientific theory we've ever developed. It describes atoms, molecules, light, semiconductors. Basically, all of modern physics and chemistry relies on it. Its incredible predictive power gives us huge confidence in principles like uncertainty.
Wow. And does this weirdness connect to things we experience more directly? Like, why is my desk solid? Does quantum mechanics play a role there too?
It does, though it's a bit more indirect and involves another related quantum rule, the Pauli exclusion principle.
Okay.
Often discussed near uncertainty, Pauli's principle says identical particles like electrons can't all cram into the same quantum state, the same energy level and location, essentially. This creates a kind of quantum pressure. It's part of why electrons and atoms arrange in shells and ultimately why matter takes up space and feels solid, preventing everything from collapsing.
So the inherent fuzziness and these quantum rules stop atoms from smushing together. Amazing.
It is. And it's such a contrast to the world of, say, Newtonian physics.
Yeah, classical physics. Like throwing a ball. If I knew exactly where it started, how fast it was going, the wind speed, gravity, I could predict exactly where it would land, right? In theory, perfect prediction.
Exactly. Deterministic. Give me the starting conditions precisely, and I'll tell you the future trajectory precisely.
But the uncertainty principle says you can't know those quantum starting conditions, position and momentum, with perfect precision simultaneously.
Correct. There's an inherent fuzziness right at the start for any quantum system. So perfect prediction, even in principle, is off the table at that level.
You know, thinking about observation changing things, it makes you wonder. Just as looking closely at an electron seems to alter its state, maybe how we focus our own attention shapes our understanding or even our experience day to day.
That's an interesting parallel. Where you direct your focus certainly changes what you perceive.
Yeah, maybe check out explorations on that theme over at Mindful Moments in our podcasts. It's an AI audiobook analysis channel on YouTube. They sometimes touch on observation and perception.
An intriguing connection. But back to the physics. It's really important not to see uncertainty as like a failure of the theory.
Right. It's not quantum mechanics is broken because it can't tell us everything.
Not at all. It's a feature, not a bug. It reflects the true probabilistic nature of the quantum world. Instead of exact outcomes, quantum mechanics gives us probabilities.
And this probabilistic nature, driven by uncertainty, is actually what allows for some really counterintuitive quantum phenomena.
Definitely. Things like quantum tunneling, where a particle can suddenly appear on the other side of a barrier it classically shouldn't have enough energy to overcome.
Like walking through a wall, sort of.
In a probabilistic sense, yes. And superposition the idea that a quantum system can be in multiple states at once until you measure it. Think Schrodinger's cat, simultaneously alive and dead. Uncertainty is fundamental to allowing these possibilities.
So even though we can't know everything about a single particle with perfect certainty,
quantum mechanics is incredibly powerful. It lets us calculate the probabilities of different outcomes with astonishing accuracy, especially when dealing with lots of particles. Think lasers, transistors, MRI machines, all rely on our ability to predict quantum behavior statistically.
Okay, so wrapping this up, we've journeyed into the quantum realm and met the uncertainty principle.
Yes, this fundamental limit. You can't simultaneously know certain pairs of properties like position and momentum with perfect arbitrary precision.
And it's more than just a measurement problem. It changes our view of reality itself, right? From a clockwork deterministic universe to one that has inherent probability and, well, fuzziness at its core.
It really does. It shows observation isn't passive at this scale, and maybe reality itself isn't as sharply defined as we assume based on our everyday world.
So here's a final thought to chew on. If observance fundamentally interacts with reality at the quantum scale, how might your own focus, your perspective, the way you observe your own life, influence the reality you experience every single day?
That's definitely something worth pondering, isn't it? the link between attention and perceived reality.
Absolutely. If this glimpse into the quantum world got you thinking, please subscribe. Maybe share it with someone else who enjoys exploring these kinds of ideas.
And if you want to go deeper, the full Feynman lectures on physics are fantastic. There should be a link in the show notes to find them.
Most importantly, keep questioning, keep exploring, keep thinking critically about the world from the incredibly tiny to the everyday.